Great. Well, I'm really happy to introduce the second of this CMU themed session. So Aida Khajavirad also finished her PhD at CMU, and she is starting her assistant professor position at Lehigh University, I guess pretty soon. She works on convexification techniques for mixed integer nonlinear optimization. Please take it away, Aida.
Great, thanks Alex for the invitation and also for the introduction. So today I'm gonna talk about the ratio cut polytope and its relationships with clustering problems, and in particular K-means clustering. And this is a joint work with Antonio de Rosa, who is a pure mathematician at Courant. All right, so what's the goal in clustering? We are given a set of data points. We would like to put them in a number of clusters based on some similarity measure. K-means clustering in particular, it's one of the oldest and perhaps one of the most popular clustering techniques, where the goal there is to put these data points in K clusters in a way that we minimize the sum of the squared Euclidean distance from each data point to its cluster center. So here you can see that like the very first formulation that one could think of to formulate this problem. It is combinatorial, and it has been shown that K-means is NP-hard even when you have only two clusters or if you are in dimension 2. There are various heuristics for this problem, like the Lyot's famous algorithm, which doesn't have any guarantee on the quality of solutions, even though it's fairly effective in practice. There are also approximation algorithms for this problem. In this talk, we are interested in the quality of convex relaxations for K-means. Now, there are different ways of formulating K-means, and based on the specific way you can formulate, you can then go ahead and construct different convex relaxations for it. Here, I'm going to talk about a reformulation, which we are going to use to present our new convexification technique. All right, so as is usually customary in this area, we try to reformulate the problem in a way that we can, we introduce some variables, we linearize the objective function, and then we move all the complexity to the feasible point. So if I do that here, you can show that K-means clustering can be equivalently written as the problem of minimizing a linear function over the set of all partition matrices, where here I denote by Z. So what's a partition matrix? Let's just illustrate it by an example. So here I have 6 data points, and I want to put them in 3 clusters. Here's an example where each color shows a different cluster. And I have the corresponding partition matrix next to it. So you can see that this matrix is a block matrix. Each block corresponds to a cluster that here, there's a correspondence between the colors. The size of each block shows you the number of points in that cluster, and each element is equal to the 1 divided by the size of that cluster. For example, the 2 by 2 blue block here tells you that in this cluster you have 2 points. It's the same for the red and same for the green. Now you can see that, okay, the problem is fairly simple. I'm minimizing a linear function over the set of all partition matrices. Now, if I want to convexify this problem, well, I can replace the requirement for Z to be a partition matrix by a bunch of valid convex or linear inequalities. So here, if I look at this partition matrix, I can immediately infer a bunch of properties. Well, it is positive semi-definite. It is component-wise non-negative. Row sums are equal to 1. The trace is equal to the number of clusters. And actually, if I just write down the properties that I told you, you get this well-known Peng-Wei's steepy relaxation of K-means. So you can see that here I exactly have positive semi-definiteness, component-wise non-negativity, well, symmetry, row sums equal to 1, and trace equal to K. Now, this STP was, presented a while ago, and it's probably the most widely used convex relaxation for K-means. It has been studied theoretically, numerically. Usually it used to be accompanied by a rounding scheme. So you solve it. If the solution is a partition matrix, you're done. If not, then you devise some rounding scheme to get a hopefully good feasible solution to the original problem. Now, what is more recent is this stream line of research in analyzing the properties of, in particular, stipular relaxations for different clustering, community detection, etc. problems, where in the data science community, where it is, they assume in addition that the input is sampled from some generative model. So why is that? Well, the argument is, so this is where things somewhat deviate from the traditional optimization way of doing things. So they say, well, you know, worst case guarantees are pessimistic. We often know how, more or less, we know how our input looks like. So it's reasonable to analyze how these algorithms would perform under untypical problem instances, where typical really is defined through some natural distribution of the input. So they make some assumption on how the input looks like, and let's say they assume there's a planted clustering, so there's a ground truth there, and then they ask under what conditions do the optimization algorithm recovers the planted cluster. And by recover, here they mean when is the planted clustering the unique optimal solution of the optimization algorithm. And why do we care about uniqueness? Well, because we want to avoid the rounding step, which often is not even clear how to do. Okay?
Aida, there's a question in the chat.
Yeah.
What is the best, from Alfredo Torico, what is the best guarantee known for this?
Yeah, so we are gonna exactly get there. Yes, that would be the next slide. Yes. All right. So actually the first question would be, okay, so what kind of random model would you assume? So that would very much depend on the exact, on the optimization problem you are looking at. So here we are looking at Kmeans clustering. So there are a bunch of random models. Perhaps the most popular one is called the stochastic ball model. So here you're assuming that the data points in each cluster come from a uniform distribution in a ball of radius 1. Okay, and then you're asking how far should those balls be so that my optimization algorithm recovers those underlying clusters with high probability. So what is high probability? It means with probability tending to 1 as the number of points that you generate go to infinity. Okay, so here again, so you have let's say K clusters. The points in each cluster are generated in a ball of unit 1. Then you denote by delta the minimum distance between these cluster centers, and you ask, what is the minimum separation distance delta between these cluster centers needed for convex relaxation to recover these clusters with high probability? So that's the question that people ask. Okay, so assume there's an underlying cluster. So assuming you know what the optimal solution is, you want to obtain conditions under which this optimal solution is in fact the optimal solution of your algorithm. Okay. So now we talk about the best guarantees for this problem. Okay, so for K-means clustering, the STP that I just showed you, this has been studied by multiple groups for K-means clustering under the stochastic ball model. So here I have actually, so here is where I listed the sufficient condition for recovery. Actually, I have 2 of such guarantees. So basically they say the STP relaxation recovers the planted clusters with high probability if, well, delta is either bigger than 2 plus k squared divided by m. Another paper shows it's 2 times the square root of 2, 1 plus 1 over square root of m. So these are 2 of the guarantees they have. There's another one. So none of these, so it's more or less they dominate each other in different regimes. Now the question is, so when you see a guarantee like this, what this really means? So there are a few observations. First, well, you see the one that depends on the number of clusters, it gets worse as you increase the number of clusters. That in fact is something one would expect. The other more interesting thing is that the recovery guarantee improves by increasing the dimension. Now, this exact recovery guarantees make sense when your balls don't interfere. Now remember, the balls have unit radius. So the best you can hope is delta bigger than 2 plus some epsilon, let's say for a small epsilon. If delta is smaller than 2, there's no hope for recovery. Okay, so if they interfere, you cannot recover. Now, so the best is 2. We don't know if that is achievable, but that's the best one can hope for. And in this recovery condition, at least in the first one, you see that if you let the dimension go to infinity, then SDP becomes optimal, right? For intermediate values, no. However, in the limit, yeah, it looks near optimal. In one of these works, they also gave a necessary condition for recovery. So which basically says the SDP relaxation does not recover the planted clusters with high probability if you have delta less than this number. Again, what does this mean? So if you put, you know, any like, let the dimension to be 2, 3, etc., it tells you if delta is a number which is strictly bigger than 2, if it's smaller than that, then you cannot recover. That imply most probably, because we don't know for sure, that the SDP is not optimal. So what do I mean by optimal? So in this context, there is this very nice question that they say, well, okay, I have an NP-hard problem. In this case, it's Kmeans clustering. Again, in the worst case, it's difficult, but now I'm doing some average case analysis, right? So the question is, take a convex relaxation. Can I show this convex relaxation under some interesting distribution on the input is as good as the original problem? So if I can show something like that, then that would be very nice, because then I can show that, yeah, under, for example, the stochastic ball model, in a bit high, the Kmeans is solvable in polynomial time, and that's a kind of result that is very interesting in this context. Now, there's another application where it's called community detection, which has to do with graph mean bisection. In fact, they can show that under a certain random model, which is of interest, SDP is as good as the original NP-hard problem in this average case sense. Here, this necessary condition kind of tells us, looks like SDP is suboptimal in this certain sense. Okay.
Aida, can I ask
yes.
a quick question? So
yes.
This is just recovering the clusters, not the actual ball centers.
So this is recovering the clusters, yes. But once you recover the clusters, so it's really like you are saying, assume, let's say this number of points are in this first clusters, the second are in the second. When do you exactly get that?
Okay, yeah.
But basically, when you recover that, you get the ball centers, right?
Well, you get the centroids of those clusters, and
yes.
you're saying that even those will converge to the gammas? With
Which gamma?
The gammas are the ball centers, right?
Yes, in the limit, yes.
Okay, so so the sufficient condition even guarantees that convergence. Okay. Okay, cool.
Okay, so now.
Aida, I have a question too.
Yeah. Yes. Hello.
I guess Alex lost the connection for a sec.
Oh. Okay.
Okay, so maybe keep going, Aida, and then he can ask you the question after.
Okay, so this is what is more or less known in terms of recovery for these SDP relaxations. There are some positive results. Still the sufficient conditions are nice. The necessary condition tells you, well, perhaps there's hope to do something better. But beyond that, as optimizers, when we see results like this, we say, well, great, but we know STPs don't scale well. Well, not as well as LPs. Can I give an LP relaxation with some nice recovery properties? That's basically the question that we're asking here. So what about LPs for Kmeans clustering? Actually, there's one result on the recovery properties for an LP relaxation, and that's as follows. So here I have the LP. As you can see, it's very easy. So you just take the SDP relaxation that we had, remove the positive semi-definiteness condition, and then replace it by these constraints that says the off diagonal should be less than or equal to diagonals. Okay? So it's an easy LP. In a way, you've made it's actually, if you write the problem as a 0-1 integer program and then relax the binary requirement, this is the LP you get. And it has been shown that this problem recovers the underlying clusters with high probability if and only if delta is bigger than 4. Now, if each ball has unit radius and you ask delta bigger than 4, it means any pair of points in the same cluster are closer to each other than a pair of points in different clusters. In this case, actually clustering is trivial. So then the conclusion in this paper was that, well, LP looks like to be useless in this context. So we said the following. So, well, I mean, this is not the most sophisticated LP you can do. If you look at the Kmeans clustering, the way I presented to you is minimize a linear function over a set of partition matrices. The convex hull is polyhedral. I should be able to do a better LP. Okay, so that's the question. So now I'm gonna present to you a better LP. So we first construct the LP, then we say what that gives us in terms of recovery under the stochastic ball model. Okay, so to construct these LPs, we kind of go back and look at the feasible region of Kmeans clustering. Before doing that, I introduce a few things to you, and then I make the connection between the two. Okay, so here we are saying, let's say I have a bunch of data points, endpoints in RM, and I want to put them in at most K clusters. So here I replaced exactly K clusters by at most, and I will tell you why shortly. So basically, I'm assuming some of the partitions can be empty. Now, for any ij between 1 to n, I define this xij to be equal to 1 over the size of the partition if points I and j are in the same cluster and 0 otherwise. Then I put all these xij's in a vector, in an n choose 2 size vector, and I call that vector a ratio cut vector. So for any partition of the endpoints, I can construct this ratio cut vector. So I refer to the convex hull of all those ratio cut vectors as the ratio cut polytope. Okay? Further, so I denote it by r cut k. So also, we denote by r cut equal k the convex hull of all the ratio cut vectors corresponding to k non-empty clusters. So all those ratio cut vectors, a subset of them correspond to k non-empty clusters. If I just take the convex hull of that subset, I get this other polytope. Okay, so why do I care about these polytopes? Well, it turns out actually, if you go back to the formulation of the Kmeans clustering I gave here, if you construct the convex hull of all of these partition matrices, and then if you project out the diagonal entries, the ZIIs, essentially you get R cut equal. So that's, in other words, if I can kind of characterize this R cut equal, I can do some lifting and I get a relaxation for my original problem. So, okay, so why do I care about the R cut itself? Well, because the ratio cut polytope is full dimensional. R cut equal is not full dimensional. And we all know that for the purpose of polyhedral studies, full dimensionality is a nice property to have. Okay, perfect. So now I define these polytopes. Well, there's no hope to characterize them in a compact way because, well, the original problem is NP hard. So what I want to do is to do a partial characterization. I want to perhaps characterize some nice class of facet-defining inequalities, and I want to get a relaxation for these polytopes, which in turn will give me a relaxation for the Kmeans problem. All right, so this next slide basically does that job for me. I'm not going to go through the details. I just tell you briefly what each proposition is. So the first proposition essentially gives me the affine hull of the smaller polytope. So I have the bigger polytope corresponding to at most K clusters, and the smaller one, which defines a facet of the bigger guy corresponding to exactly K clusters. The first proposition gives me what the affine hull of that guy is. The second proposition tells me, you know, the inequality xi greater than or equal to 0. Well, that's a very trivial inequality. It is in fact facet defining if and only if you have at least 3 clusters. And the most important one is the last proposition, which gives you this new class of facet defining inequalities, which I will show you in the next slide. It's kind of a generalization of triangle inequalities for the cut polytope, which is the reason we even call this polytope the ratio cut polytope. Okay, so let's perhaps go to the next slide and talk about this last class. Okay, so now what I basically do is I introduce these auxiliary variables, which correspond to the diagonal entries in my partition matrix, so XLL. So if I introduce them and I rewrite the inequalities that I had in the previous slide, which I kind of have shown but not here, that they are facet defining already, I get this different representation for these inequalities. Okay, now for simplicity, let K be equal to 2. So in the case of two clusters, these inequalities can be written in this simple form. Not this form. If you have seen the Boolean quadratic polytope or the cut polytope, this is very familiar, in fact. If xii is replaced by 1, in fact, you get the triangle inequalities. So let's back up a bit. So to study the max cut, we define a cut vector as follows. We say, given 2 points, if they are in the same partition, let xij be equal to 1. If they're indifferent, let them to be 0. That's a cut vector. The convex hull of all the cut vectors is the cut polytope. And then these so-called triangle inequalities are facet defining for the cut polytope. Now I argue this new class that I defined here for the ratio cut polytope can be considered as an equivalent of this first type of triangle inequalities. What's the difference? Well, here I have a 1, there I have an xii. So what about the second? So xij plus xik plus xjk greater than or equal to 1. I would argue the first inequality that I showed in the first proposition is the equivalent in the ratio cut context. So there are some similarities, but there is a fundamental difference here. So if you have read about cut polytope has this very nice property which is called the zero lifting. Ratio cut polytope does not have that. Why doesn't it have that property? Because we care about the size of the clusters. And therefore, when you add the number of points, the structure of the ratio cut vectors or the vertices of your polytope changes. And that is in fact hidden in this xii. So here, this inequality looks sparse to you because I did this lifting, but in fact, if you write it in the original space, it depends on all those xij's. So between the cut polytope and ratio cut polytope, there are very nice similarities, but also fundamental differences. So that's the point I wanted to make here. Okay, now I gave these new classes of facet defining inequalities. I can define a relaxation for the ratio cut polytope. And I denote this relaxation by rmet and rmet equal because this relaxation is similar to the metric polytope in the cut polytope literature, which consists of all the triangle inequalities. In that literature, we know that the metric polytope coincides with the cut polytope if and only if n is less than or equal to 4. In fact, we have the same result here. Now, n equal to 3 or 4, it's not a big deal. However, this polytope this relaxation has the following nice structure. Even though for n equal to 5 or bigger, it's not the convex hull. However, every vertex of my convex hull or every ratio cut vector remains the vertex of my new relaxation. So my new relaxation obviously has many more vertices, but all the original vertices remain vertices of the new one. Again, you have something similar in the context of cut polytope. All right, so now we have this new LP. I think I should wrap up soon. So I have this new LP for Kmeans clustering. We want to understand its recovery properties, let's say under the stochastic ball model. Okay, so how would we do that? Well, let's assume that we only have K clusters. That's what we have a result for. One would like to do it for a general number of clusters, but we don't have that result yet. Okay, so now I have 2 clusters. I have written the primal here and the dual, and I assume the following planted model. So I assume that the first half of so I assume I have even number of points. The first half of the points are in the first cluster. The second half are in the second cluster. Therefore, so again, when I say I make this assumption, I assume this is what I want to recover. So I assume this is the optimal solution to the primal. I want to see under what conditions it actually is. Okay. So, well, that's simple to do. All I need to do is find a dual feasible point, lambda, mu, omega, for which strong duality is attained. Okay. So to do that, so basically here we have the recovery guarantee. Again, I don't have the time to go over what it means, but it's basically the inequality I have here. It's deterministic. It does not depend on any stochastic model. Basically, it tells you that that planted cluster corresponds to an optimal solution of the LP if you have this inequality for all ij's in each cluster. And again, what does this inequality mean? It just tells you how much closer the points in each cluster should be compared to the points in different clusters. You could interpret it more concretely, but we don't have the time. So, and again, for now, let's take this as a deterministic guarantee. And now I show you what it actually means under a random model. Okay, so we have a deterministic guarantee that guarantees optimality of the planted cluster. Okay, now I want to go back to the random model. So for the random model, what should we do? So from deterministic to the random model, basically now we plug in this random model that we have assumed, and we already and what we are able to do is to show that the LP relaxation recovers the planted clusters with high probability, provided that delta is bigger than 1 plus square root of 3. Okay, so how to go from deterministic to these results? There are multiple probabilistic, so maybe I can say just in 2 sentences. So you have a deterministic recovery condition. So what you do first is to show that using some concentration inequalities, you show that that condition holds with high probability if it's valid in expectation. So valid in expectation means that from the discrete model, you can go to the continuous model. Once you go to the continuous model, then you can solve it and get this result. And I'm obviously skipping a lot of steps here, but this is the final result you have. So, but let's understand what it means. So first of all, 1 plus the square root of 3 is more or less 2.73. Remember that the recovery result for that LP was 4. So this is already much, much better. How good is it? Well, it is tight if you're in dimension 1. So meaning that the original K-means can recover with high probability in dimension 1 if delta is 1 plus square root of 3. How does it compare with SDP? Well, here is the best recovery result for case of 2 clusters for SDP is delta bigger than 2 plus 4 divided by m, where again m is dimension. So for the dimension bigger than or equal to 6, the SDP is better. So one thing that we don't like here is obviously that our recovery result is not improving by the dimension, right? So we have more sophisticated deterministic recovery guarantees that we are not able to analytically solve under the stochastic wall model. However, we are able to show by simulation that they improve by dimension. Therefore, this no independence on the condition is not a limitation of the LP. This is just a limitation of our deterministic guarantee that we analyzed. Okay, so the bottom line is on the theoretical side, there's a lot to be done. Sufficient guarantee that we gave, even though it's much better than the existing LP, it is very conservative. So there's a lot of room for improvement. It is very possible that LP also has this near optimal property of the SDP in very high dimensions. We don't know how to do it exactly yet, but there's nothing that suggests we can't do it. So at the end, I just show you in a minute some numerical results, just to compare the LP and SDP for some random instances. So in this first slide, I'm assuming that the data points in each cluster are generated on a unit sphere, not a ball sphere. Then I consider the following 4 configurations. The number of clusters can be 2 or 3, and the dimension can be 2 or 3. Then for each configuration, I change delta. I start from 2, which is the minimum that you can hope for recovery, and I keep increasing it. For each fixed delta, I do 20 random runs for each run, and then I count the number of runs among the 20 for which the optimization algorithm returns the planted cluster as the optimal solution. And then I divide it by 20, I get the empirical recovery rate. So you can see the blue dots are the LP and the red is SDP. So you can see in all these 4, LP is much better than the SDP. Also, as you increase the dimension, LP improves, which makes us think that we need to improve our recovery condition. And as you expect, as you increase the number of clusters, things get worse, but that's just expected. And finally, in the last slide, we do the same computation, but this time for the stochastic ball model. So this time the points are generated in each cluster uniformly in a ball of radius 1. Again, LP significantly better than SDP. So again, here, you know, this is just a new direction we have started. There are many open questions. You would like to know better recovery conditions for K clusters. We want to understand how the LP really behaves in high dimension. But these, at least preliminary results suggest that this LP relaxation we are looking at has nice properties under these random models. Right, that's it.
Thank you, Aida. And in the interest of time, let's take the questions to the breakout rooms. There were a few in the chat that might be still asked. Now, I also want to say that next week we're going to have another discrete optimization talk session. We're going to have Yannis Kurtz give a talk for half an hour, and then we're going to have half an hour, kind of a social hour, half hour, and also time for, we'd like to solicit some feedback for the format of dots coming up in the academic year. We're going to take a little bit of a summer break after next week's session for a few weeks, and then start back up sometime in August, maybe. We haven't decided yet exactly. So I'd like you all to join us there. And also, as usual, I want to pitch the Discord, which is for, if you can't stick around right now to ask questions and like to participate in the discrete optimization community and talk to people informally, there's this Discord channel, which I will post in the chat now. And I encourage everyone to join and post if you have results, questions, anything like that, participate there. So with that, I'd like to thank both Amitabh and Aida again, and we'll move to the breakout rooms.
Thank you.